So now that we have covered differential and integrated rate laws, I would like to put our knowledge into practice and do some rate law problems. Just to review, in the last lecture, I gave you a kind of summary chart that gives you a lot of information about differential and integrated rate laws for zeroth order, first order, and second order chemical reactions. So this is available to you as a handout posted on Blackboard in the Chapter 11 folder, and it's really useful for doing problems. So let's use it to solve this problem here first. In this example, we have CH3NO2 decomposing by a first order rate law. If we know the rate constant, K equals 0.0170 reciprocal minutes, and we know the initial concentration of the reactant to be 0.4 molar, can we figure out what is the concentration of it after 15 minutes? All right, so our big clue here is first order rate law. So we are going to need to go back to our integrated rate laws and find the first order integrated rate laws. Now we have it in a couple of forms, and there's a little typo in this. This is supposed to say natural log, but for some reason the font changed it to a number one. So that's natural log. So I'm gonna take the form of it that we derived in the previous one using the natural logs. Um, we know that the time t that we want here is 15 minutes because we want to know what the concentration is at time t, 15 minutes. Now, the rate law that we want to use is the first order rate law. This is just a form of it, just rearranged using the law of logs. You can use any form of it you want, as long as you do the algebra consistently. So the natural log of the initial concentration over the concentration at time t is equal to kT. I know the initial concentration. It was given to me in the problem. It was 0.4, so 0.400. The concentration at time t, instead of A, I'm going to put in CH3NO2, which is my actual reactant here. This is going to be equal to K. K was given in the problem, 0.0170 reciprocal minutes. And I want to make sure I have the same units for time, 15 minutes. So the units of time will cancel, so I have unitless quantities on both sides. And that product comes out to be 0.255. Now, to get rid of the natural logs, I can raise e to the power of both sides. So e to the natural log of 0.4 over x, essentially, and x is CH3NO2, is going to be equal to e to the 0.255. Now, the e and the natural log cancel, so this simplifies to 0.400 over the concentration of the reactant CH3NO2. If I plug e to the 0.255 into the calculator spits out 1.29. So you should pause here and make sure that you can do that. Rearranging to solve for the concentration of the reactant at time t, I find that it's 0.310 molar. And you should get a number that makes sense, right? We start out with 0.4 molar, so at time t, after 15 minutes, that should decrease. So this is a plausible number after some of the reactant has been consumed. We are down to 0.310 molar. Let me ask you now a follow-up question, another type of question that you may potentially see in the kinetics chapter. How long does it take for the concentration of the reactant to drop to 0.1 molar? Let's say 0.100 molar. All right, so we know that after 15 minutes, it drops from 0.400 molar to 0.310 molar. So now how long does it take to drop to 1 molar? Well, there we can take the same integrated rate law that we used here and plug in the initial concentration and plug in the final concentration and then solve for T. So let's do that. The natural log of the initial concentration over the final concentration at time t is equal to kT. We know K is equal to 0.0170 reciprocal minutes. It's a rate constant. And we want to solve for T. So this is easy enough. I just need to take the quotient, 0.4 divided by 0.1, take the natural log of that, and then divide it by K, and I should be able to solve for T. T is 81.6 minutes. So that's telling us that it takes 81.6, or I guess I should round it to 82 minutes to match the 15. It takes about 82 minutes for the reactant to drop from 0.4 molar to 0.1 molar. So this is a plausible number. All right. So I suggest that you pause and make sure you understand that problem before we proceed on to the next problem. In the next problem, I would like you to consider a reaction where C2H5OH, that's ethanol, decomposes to C2H4 rather, and water. Okay. So for this reaction, data were collected very hot, 600 Kelvin. And the data that were collected gave a plot of the concentration of ethanol versus time with a straight line. The slope of the plot is negative 4.10 to the minus 5. So the negative straight line slope is telling us that I get that negative straight line when I plot the concentration versus time. So this is the concentration of C2H5OH. And on the x-axis, I have time. So they are indirectly telling me what order this reaction is. Let's go all the way back up to my cheat sheet with the rate laws. Let me clean this up a little bit. I am looking for a situation where my straight line plot has just plain old concentration on the y-axis versus time, giving a straight line with a negative slope. So the only situation where I have that concentration with a straight line with a negative slope is when I have a 0th order reaction. And for a 0th order reaction, the differential rate law is just rate equals K. And the integrated rate law is that the concentration of A at time t equals A0 minus KT. It can't possibly be the first order or the second order reactions because the y-axes for the straight line plots are different for those. For the first order, I need the natural log, and for the second order, I need the reciprocal. So I know that I'm dealing with a 0th order reaction. That is what this is telling me. N equals 0. Therefore, N equals 0. So what am I asked to do? I am asked in this problem to determine the rate law, the integrated rate law, and the rate constant K. Well, that's very easy. I can just get them from the chart. If N equals 0, that means that the rate is equal to K times the concentration of A. Actually, instead of writing A, I'm going to write the concentration of the actual reactant, which is ethanol, raised to the 0th power, because N equals 0. Of course, anything raised to the 0 power is 1. So the rate law is just simply that the rate equals K. The integrated rate law is A at time t equals A0 minus KT. Another way of writing that would be C2H5OH at time t equals the initial concentration, C2H5OH sub 0, minus KT. So this would be the integrated rate law. Okay, the top one is the differential rate law. This is the integrated rate law. Finally, the rate constant K I get from the slope. So the slope of the line is equal to negative K. And that means K is always going to be positive. So the K value is positive 4 times 10 to the minus 5 moles per liter seconds. All right, so that was straightforward. I can do that part of the problem simply enough by looking up my rate law information. Now let's do some plugging in with actual data. In part B of this problem, I am asked if the initial concentration, so A0 effectively, but the initial concentration of ethanol was 1.25 times 10 to the minus 2 molar, calculate the half-life. Okay, so I can also go up to my little cheat sheet to get the half-life for a zeroth order reaction. T1 half, the half-life equals A0 over 2K. So let's use that expression for the half-life of a zeroth order reaction to solve this problem. T1 half equals the initial concentration of ethanol over 2K. My initial concentration is given in the problem, 1.25 times 10 to the minus 2 moles per liter. And I put it over 2 times K. The K value is 4 times 10 to the minus 5 mole per liter seconds. So notice what happens here. The moles cancel, the liters cancel, the seconds flip to the top. And once you do all of the arithmetic, you should get an answer of 156 seconds. So that's the half-life for this reaction when the initial concentration is 1.25 times 10 to the minus 2 molar. Literally, what the half-life means is the amount of time it takes to consume half of the reactant. Finally, how much time is required for all of the 1.25 times 10 to the minus 2 molar ethanol to decompose? And here, I'm going to need my integrated rate law that I wrote down for part A. Okay, I can use that integrated rate law to solve this problem. So for my, so I can actually, you know what I'm going to do? I'm going to just select this and copy it and bring it down so that we can use it for this problem. And plug in the numbers. So what do we plug in? We know that the initial concentration of ethanol is 1.25 times 10 to the minus 2 molar. I know what K is. I want to figure out what T is. So the question is, what is the concentration at time T? Well, if we want all of it to decompose, the concentration at time T must be 0. So I'm going to plug in 0 molar equals 1.25 times 10 to the minus 2 molar minus K. K here is my K is positive 4 times 10 to the minus 5 moles per liter seconds. And I'm going to multiply that by my T, and T is my unknown that I'm looking to solve for. So if you do the algebra here and solve for T, you should be able to get a T that is 313 seconds. The units come from the denominator of K here. So this is going to be how much time it takes for all of the ethanol to decompose. Now, just a word of warning, if you guys are doing problems like these and you get a negative time, then you might want to go back and make sure you didn't make a sign error somewhere along the way. Okay, so I recommend that you go back and do the algebra and make sure that you can get the same answers as in this video.